Hi, I'm John. I want to talk about the multiplier board I designed for the PJ5 CPU. So, the way this works is there are four different buses that come in here. They're all 8-bit buses. There are two inputs which usually come from registers called register bus A and register bus B, very unimaginatively. There's also two outputs. One of them is the register write bus, and the other one is a special bus that only goes to a special register, which is called register ZH. And that allows us to have a 16-bit result from the multiplier and store the whole thing. So you get two numbers coming in, 8-bit by 8-bit, and you get a 16-bit output. It doesn't matter if you want to do signed or unsigned multipliers. It happens that actually, as far as the logic is concerned, they're exactly the same. If you interpret the input numbers as signed, then you interpret the output number as signed and you'll get the right value. So the values come in. The first thing there is this thing here, which is marked layer 0, which is a bunch of AND gates. Now each of these chips has 4 AND gates on it. And what this is doing is it's taking one of the 8-bit inputs, and it's doing a bunch of effectively multiplying by 1 bit of the other input. And that gives us a 8-bit output which can have some values in it and a whole bunch of bits that are 0. So the output of this is a whole bunch of bits which might not be 0. And for each bit we know what position it is. And then basically all we have to do is add them all up. So what we do at each level, so we pick 4 bits from one set of AND gates, or possibly even from different AND gates, it doesn't matter. We pick another 4 bits that are held the same positions in the output, and we use an adder chip like this one. These are the first level of adders. We use these adder chips to add them up. And fairly obviously, this adder probably takes its input from these two mostly, and this adder takes its inputs from these two mostly, but there are traces that run all around here to get signals to where they need to be. It's not quite as simple as just coming next to each other. The adders, so you actually get a carry in as well, so it's actually a 5-bit input to each of these adders, and there's a carry out, so it's a 5-bit output. So 5-bit plus 4 bits in, 5 bits out. The outputs of these adders, some of the signals that perhaps didn't get added the first time, go on to the next level. This is layer 2. And the adders there add up some more bits that have come in from the level 1 adders. I ought to clarify, these are level 1A and 1B, that it's actually the same sort of layer of adders. These take inputs directly from the AND gates. But just for board layout, they ended up getting split to keep the traces short. So anyway, layer 2 adds those bits up, and then they come over to here. We have layer 3, which again adds them up. Some of these intermediate outputs that are coming in here, we also print out and we show in these LEDs. So each of these LEDs is one of the bits that are coming in at the coming out from layer 2 into layer 3. So layer 3, we add them up, and then the outputs from layer 3 go off to layer 4, and then the outputs from layer 4 adders go out to just a buffer, which, 2 sets of 8-bit buffers, which then output to the 2 buses. In terms of getting this fast, the most important thing is to reduce the longest path. So the longest path that any signal takes is through one of these AND gates, through one of the level 4 adders, through one of the layer 2 adders, through one of the layer 3 adders, and then through each of these level 4 adders in turn. So if you look at the data sheets for the maximum delay, you can find out the maximum delay for these AND gates. You can find out the maximum delay for the adders, and you multiply the maximum delays for the adders by 1, 2, 3, 4, 5, 6, and that gives you the maximum, add on the maximum delay for the gates, and that gives you the maximum delay for the circuit. And if you want to know the frequency it'll run at, the absolute maximum this can run at, if everything else in the system was instant, is 1 divided by whatever that delay is. And I've very deliberately chosen fast chips here. These are S grade. Actually, I can't remember if they're S or F grade adders, but they're one of the really fast adder families that uses a lot of power, but is also insanely fast. None of this, low power CMOS stuff. These are big fast industrial grade. Let's use lots of power chips. And there has been a lot of very careful selection of which bits to add at each level. So if you've got a bit, you don't want to choose the wrong bits and then have to add more layers of adders. And there's been a bunch of optimization to try and pick the optimal bits to add at each level. This is based on the Wallace tree design, which doesn't use 4-bit adders, it uses 1-bit adders, which is great if you're doing a hardware silicon design, but is not what we're working with here. We're working with 5 plus 4-bit adders, which is a different kettle of fish. So that's it. That's my multiplier board, and as you can see, it works. It works reasonably fast, and it seems to be reliable. We've not done exhaustive testing yet. Exhaustive testing will wait until we've got the rest of the system up and we can, make it go through a counter loop and test everything that way. But for now, it seems to be working well.